In the previous video, we finished our discussion of colligative properties. Today, we'll dive into the microscopic dynamics of solvation. The word solvation is the technical term used to describe the creation of a solution by dissolving a solute in a solvent. The point of this video is to break down what exactly happens at the molecular level when a solution is made. To put it another way, we're going to look at how solutions form. To do this, we have to understand how solute molecules interact with solvent molecules. We already talked about this a little earlier in this unit, so today we'll go into more detail. We're also going to talk about the differences between dissolving ionic compounds in a solution and dissolving covalent compounds in a solution. When it's all said and done, solutions form in a two-step process. First, the attractive forces between individual solute molecules must be broken. At the same time, the attractive forces between individual solvent molecules must be broken. Only after this happens can we move on to our second step, which is for solvent molecules to establish attractive forces with solute molecules and thereby form a solution. That's a lot of big words there, but we can understand this a little better by looking at point number 4 here. There are essentially two types of attractive forces that exist between atoms. By attractive forces, we mean forces that hold atoms together. This is a crucial concept. If atoms weren't able to hold together, we wouldn't have matter as we know it. Think about what would happen if all the atoms in a chair were to start drifting apart rather than holding together. The chair would fall apart, cease to exist. Atoms being able to attract one another and adhere to one another is why we have the universe that we do. Now, as we said before, there are two types of such forces. The first type is called cohesion. Cohesion is the force that exists between like atoms, or atoms of the same element or compound. So, for example, gold atoms in a bar of gold tend to stick to other gold atoms in said bar. This cohesion is what allows the gold bar to hold together instead of evaporating into a bunch of disparate gold atoms. In the same way, water molecules like to stick together, and this is why it's possible for there to be puddles and lakes and oceans and other bodies of water in which trillions of water molecules are present in the same general area. Adhesion, by contrast, is the attractive force that exists between different atoms, atoms of different elements or compounds. Essentially, what we're trying to say here is that in order to make a solution, the first step is to break the cohesion between solute molecules as well as the cohesion between solvent molecules. The second step is to establish adhesion between solute and solvent molecules. If we remember back to an earlier unit, intermolecular forces like hydrogen bonding and dispersion forces are responsible for both cohesion and adhesion. Solvation, as we've already established, is the process of creating a solution by combining a solute with a solvent. In the context of solvation, cohesion is referred to simply as the attractive force, whereas adhesion is called the solvation force. When a solute has a high solubility in a specific solvent, we can conclude that the solvation force is stronger than the attractive force. In other words, solute molecules would rather adhere to solvent molecules than to their fellow solute molecules. For something to be soluble in, say, water, means that the solute molecules have a stronger attraction to the water molecules than they do to their fellow solute molecules. This is the principle that determines whether or not a given solute is soluble in a given solvent. Here's a visual representation of solubility. On the left-hand side of the screen, we have our solute, as represented by the blue dots, and our solvent, as represented by the red dots contained in a box-like container. Let's say we add the solute to the solvent. If we were able to zoom in on the molecular level and see what's happening between the solute molecules and the solvent molecules, we would see something like the picture on the right. The solute molecules have separated from each other and are floating freely in the solvent molecules, which have also separated from each other in favor of interacting and forming intermolecular forces with the newly added solute molecules. In this instance, we would say that the blue solute is soluble in the red solvent. This depiction shows the opposite scenario. Here, the solute molecules are more attracted to each other than they are to the solvent molecules. Thus, they remain together in a sort of clump at the bottom of the container. For this case, we would say that the solute is insoluble in the solvent, since the cohesion between the solute molecules has not been destroyed. It is, of course, impossible to predict solubilities for each and every combination of solute and solvent, so chemists must rely on generalized rules of thumb instead. The first and simplest case is for an ionic compound dissolved into a solvent. When ionic compounds are added to a solution, they separate into their constituent ions, their cations as well as their anions. For example, adding salt to water causes the sodium chloride to divide into sodium cations and chlorine anions. These ions are then allowed to float freely in the water, creating the solution we know as salt water. This is an example of an ionic solution, and such solutions are very good at conducting electricity. What we mean by this is that electrical charge can travel easily through salt water, meaning that if a person were to be standing in salt water and then the salt water was struck by lightning, there's a good chance that the person in question would be electrocuted by the movement of the electricity through the salt water. The same thing would happen if they were standing on a big block of metal, since metals also allow electricity to pass through. But if the person were standing on a block of wood, they would not be electrocuted, since wood is not a good conductor of electricity. Since ionic solutions are good conductors of electricity, the solutes involved in these solutions are called electrolytes. Electrolytes are classified as either strong or weak. Strong electrolytes are so named because they completely disassociate into their constituent ions when dissolved in a solution. Weak electrolytes do not do this. Sodium chloride is described as a strong electrolyte because when it is dissolved in water, all of the sodium chloride molecules will split into sodium cations and chlorine anions. Of course, there is a limit to how much salt we can dissolve in water, and once we reach that limit, no more salt will dissolve. But that's not what we mean by a strong electrolyte. So long as the concentration of sodium chloride in the water is below the solubility, all the salt molecules will split into cations and anions. This is what the word disassociate means in this context. A weak electrolyte won't do this. Even while we are under the solubility limit, some of the weak electrolyte molecules will fail to disassociate into cations and anions. This means that there are less ions in the solution overall, and as we can probably imagine, this means that less electricity is able to travel through it. There are some substances which don't split into cations and anions at all when dissolved in water, and these substances are called non-electrolytes. Sugar is one example. Sugar, or sucrose, is a covalent compound, so it's not going to split into ions when we dissolve it in water or some other solvent, as the case may be. When covalent compounds are dissolved in a solvent, the destruction of cohesion is not strong enough to break the covalent bonds holding the solute molecules together. Because of this, the covalent solute will split into individual molecules that will then freely float in the solvent. It will not, however, split into individual atoms or ions. There's also no general rule of thumb that we can use to predict whether or not a particular covalent compound will be soluble in a given solvent. For ionic compounds, they tend to be soluble in polar solvents, since the molecules of a polar solvent will have one end with a slight negative charge and one with a slight positive charge due to the disparity in electronegativities between atoms in the molecule. We discussed this in detail in our video on polarity if you'd like to go back and review that. When an ionic compound is dissolved in a polar solute, it disassociates into cations and anions. Cations have a positive charge, so they are attracted to the negative end of the solvent molecules. Anions have a negative charge, so they are attracted to the positive end of the solvent molecules. This attraction allows the solvation force to become stronger than the cohesion between solute molecules, and this is why ionic compounds tend to be soluble in polar solvents. Predicting the solubilities of covalent compounds is trickier, since it involves looking at the molecular structures of solute and solvent. This becomes especially pertinent in organic chemistry, but we're not going to look much at it here. For our purposes, it's enough to remind ourselves that like dissolves like. Polar compounds, which ionic compounds are, tend to dissolve in polar solvents. Nonpolar compounds, meanwhile, tend to dissolve in nonpolar solvents. These are trends, rules of thumb, so we shouldn't expect them to hold true in every case, but for general use, this usually suffices. One conceptual problem before we end for today. Water is often referred to as the universal solvent due to its ability to dissolve a wide range of solutes. Speculate on possible reasons for this. First of all, we know that water is a polar covalent molecule, which means that any amount of water will be a polar solvent. Oxygen is quite a bit more electronegative than hydrogen, which creates a slight negative charge on the oxygen atom and slight positive charges on both of the two hydrogens. This polarity allows it to dissolve ionic solutes using the mechanism we just finished talking about. Because water is ultimately a polar covalent compound, however, it is also capable of dissolving polar covalent solutes by forming hydrogen bonds. This means that out of the three general classes of compounds as classified by polarity, ionic compounds, polar covalent compounds, and nonpolar covalent compounds, only nonpolar covalent compounds are excluded from being soluble in water. Methane, or CH4, is one example of a nonpolar covalent compound that has quite a low solubility in water. In the next video, Unit 4, Video 7, we will close out this unit by talking about solution stoichiometry. Thank you for watching.